In this video, we are going to introduce the moment of inertia and angular momentum. The learning objectives are to define the moment of inertia and angular momentum, and then to relate them to the linear motion. So, why are we doing this? Well, because we are familiar with the motion in 1D or in 3D of particles, but maybe we're a little bit less familiar with the motion around a sphere or in a circle. And those are kinds of motion that we're going to encounter often when we look at a diatomic molecule that tumbles in space, or, for example, an electron that rotates around a nucleus. So we need to identify important components that we're going to use later in those problems. So first of all, we're going to begin with the linear motion that we are all familiar with. So if we have a particle of mass m that moves at a velocity v, we know how to calculate the linear momentum of that particle, which is just the mass times its velocity, and we know how to calculate the kinetic energy of that particle, which is just 1/2 the mass times the velocity squared, which is the same as the momentum squared over 2m. So this is something that we are already familiar with. The goal is to identify similar things for a rotational motion and see if we can relate to the linear motion what we find. So we're going to look here in just 2D system. We can extend this easily to 3D. So in 2D we have a particle of mass m that is rotating on a circle with a radius r, and it's rotating with an angular velocity omega, which we know is 2 pi, the frequency, and it's going to have a certain velocity. What's that velocity? It's just the distance that the particle covers, so the whole radius, over the time that it takes to cover that. So what is the distance? Well, the distance is 2 pi r, so that's that distance, over the time. What's the time? It's the period. This is the period, this is the kinetic energy. We're using the same symbol, but so what's the period? It's 1 over the frequency. So we have that the velocity is 2 pi r frequency. And we know that 2 pi times frequency is omega. So the velocity of the particle is just omega r. All right. Now, let's see if we can find something that allows us to relate to the kinetic energy. Well, what's the kinetic energy of that thing? Again, the formula is the same. It's just 1/2 the mass times the velocity squared. But now we know what the velocity is, so it's going to be just 1/2 mass, and the velocity is omega r squared, so it's going to be omega squared r squared. Now we introduce the concept of moment of inertia. The letter is capital I, and the definition is just the mass times the square of the radius. And if we want to picture what this moment of inertia is in something that we are maybe more familiar with, if we think of figure skating and figure skaters, and they keep their arms extended, they have a big moment of inertia because this r is larger, and the moment of inertia goes with the square of the r. As soon as they close the arms, their moment of inertia remains the same, and because the angular momentum is conserved, all of a sudden their speed is going to go up. So that's why they can do those fancy things. It's physics. So now, having just introduced the moment of inertia, we can substitute that into this equation and figure out that the kinetic energy is just 1/2 I omega squared. And now we can start drawing the first parallels between the linear motion and the angular motion. If we look at this equation in this form here and the equation in this form here, we can see that we have the 1/2 and the 1/2, that we have the velocity square, here we have the angular velocity square, and here we have the mass, and here we have the moment of inertia. So there is a nice table on chapter 4 of the book, and these comparisons are made there for us. So we can see that the mass in linear motion corresponds to the moment of inertia. In angular motion, the speed to the angular speed, and we also see that the kinetic energy can be expressed in these forms, and so far we have looked at one of these forms, which is this one over here. We have almost all of the pieces there. Now we just need to figure out one that is still missing, because we know the momentum, the linear momentum in linear motion, so there must be something similar to linear momentum in angular motion. So if we say that m, we call it I, we found that analogy, and the velocity is the angular velocity, then there is going to be something in angular motion that is conceptually similar to linear momentum in linear motion, that is the product of those two things, just like that. That thing is the angular momentum, and the letter that represents it, the angular momentum, is capital I, and it's just the product of the moment of inertia times the angular velocity. Let's check if we can continue the parallel using that definition of angular momentum. If I multiply in this equation both the numerator and the denominator by I can write 1/2 I omega squared over I. And that would be, just because I omega is just L, it's going to be L squared over 2I, which is exactly the same form that we have here. So to summarize what we've done, we have introduced the moment of inertia, and we have drawn parallels between the linear motion and the angular motion, and we found that there are analogous expressions in rotational motion to express similar quantities as kinetic energy and linear momentum in rotational motion. So we have also kinetic energy, and it's not linear momentum anymore, it's going to be angular momentum. And this table summarizes all of our findings.